Today we are going to develop and apply the general multiplication rule for probability. But first, a warm-up. Turn to page 36, pause the video here, and try this, all three questions now. Okay, so the common, actually, let me show you the answers. Here are the answers. We've got part A, part B, part C. And a common question is for part C with the or. So let me go back up to the data. And for the or, the probability that it was defective plus the probability that it was in the evening, but we have to subtract the probability of defective and evening because that would have been used twice. So defective is 85 out of 600. The evening is 240 out of 600. The defective and evening is 25 out of 600. So this is one possible way to get the 300 out of 600. Another way is to just add separately. So you could do defective, 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 and then any missing evening you hadn't done yet. So 20, 25, 40, and 215 would also add up to 300. And then for part C, the definition of independent events, the probability that defective, so that's probability of defective, and compare that to defective given that they were made at night. So if I choose defective as the probability by itself, then I have to compare that to the conditional of defective given night. If for some reason you did probability at night as the solo event, then you would have to compare that to night given defective. So here's my work doing it this first way. Defective is 85 out of 600. That's the total here. Defective given that night is the 40 out of the total night, which is 140. Because these percents are not equal, the events are, because they're not equal, they're not independent. It means that being produced at night changes the outcome of being defective or not. Okay, so turn to page 37. Read along with me about cereal. A cereal company puts one of the following toys in cereal boxes: a block, a toy watch, a ring, or a toy airplane. The machine that places the toy in the box is programmed to select a toy by drawing a random number of 1 to 4. If 1 is selected, a block is put. If 2 is selected, a watch is put in the box. 3 would be a ring, and 4 would be an airplane. When this promotion was launched, young children really wanted to get the airplane. If you bought a box of cereal, what is your estimate of the probability of getting the toy airplane? Pause the video and write down your probability and reason. It is a 1 out of 4 chance. Airplane is 1 toy out of 4 possible toys. If you bought a second box of cereal, what is your estimate that you would get a toy airplane in the second box? That's still 1 out of 4. Your first box does not change your second box. The machine is not changing its random numbers based on what box it's filling. List all the possibilities of getting the 2 toys. Okay, so we had B was for block. R is for ring. Oh, I forgot. W is for watch. And we'll do A for airplane. All right, so in the first box of cereal, I could get a block, and then a block in the second. I could get a block and then a ring. I could get a block and then a watch. I could get a block and then an airplane. In the next box, I can get a ring and a block. I can get a ring and a ring and a watch, a ring and an airplane, or we could get a watch and a block, a watch and a ring, a watch and a watch, a watch and an airplane, and then lastly, it would be an airplane and block, airplane and ring, airplane then watch, airplane and then airplane. Whew, that's all the possibilities. That's our sample space. Based on the sample space that we created, what do you think the probability of each of the following outcomes is if 2 cereal boxes are purchases? So pause the video here, look at your sample space, and answer all of number 4, parts A through F. So I brought my sample space over, and if I count up how many have only one airplane, that'd be 1, 2, 3, 4, 5, that is 6 airplanes out of 16 total events. At least one airplane means 1 or 2 airplanes. So I have the 6 with just 1, but then I can also include a double airplane, so that's 7 out of 16 events. No airplanes. Well, if 7 have at least 1 airplane, to get the other events that are no airplanes, that's 9 out of 16. So you could add 1, 2, 3, 4, 5, 6, 7, 8, 9. An airplane in the first box, so that is 4 out of 16. Could also reduce that. Could reduce this one too. An airplane in the second box, that is 4 out of 16 here, which reduces. And an airplane in both is just 1 out of the 16 events. Are the events independent or dependent? So let's see, what is the probability of an airplane in the first box? Compare that to the probability, now let's go with the second box, of an airplane in the second box, given that there is an airplane in the first box. So an airplane in the second box, we got that here, it was 1 over 4. Given a second airplane, given it was in the first box, so that given that reduces us just to this sample space of 4 events. And the airplane in the first, airplane in the second box, given that it was in the first, so that's just this last, that's 1 out of those 4. These are now equal. These are equal probabilities, so they are independent events. Which probability rule applies? So if we compare, if I look here at both cereal boxes, airplane in the first box, probability of airplane in the second box, if I look at them, this was 1 out of 4, this was 1 out of 4. If I multiply, we get that 1 out of 16, like we got here, by looking at our sample space. This only applies if events are independent. So the probability of A and B equals the probability of A times the probability of B if the events are independent. All right, so let's now talk about chocolates on page 39. Do you remember the famous line, "Life is like a box of chocolates" from the movie Forrest Gump? When you take a piece of chocolate from a box, you never quite know what's going to be inside it, what the chocolate will be filled with. Suppose you take a box of chocolates that contains 15 identical pieces. 3 are caramel, 2 are cherry cream, 2 are coconut, 4 are chocolate whip, 4 are fudge. If you randomly select one piece from the box, what is the probability it will be filled with fudge? There's 4 fudge, so that's 4 out of 15 pieces. Suppose the type of filling is named underneath each piece, and you don't like fudge, so you put it back without biting into it, and then randomly select another. What's the probability that you select a piece filled with caramel? That's 3. All the pieces are back, so that is 3 out of 15 chocolates. So since you put back the chocolate, that's called with replacement. If A1 is the event of picking a fudge, and B2 is the event of picking a caramel, on the second selection, what is the probability of picking A1 and B2? So fudge, this was fudge. This is caramel. With replacement. So does looking at the fudge first change the outcome of getting a caramel second? It does not. Replacement means independent. Because they're independent, we can do 4 out of 15 times 3 out of 15, the 2 probabilities we found out here. That's 12 out of 225. We already said they're independent because of the replacement. If instead you randomly select a second piece of chocolate after you ate the fudge one, so you've already eaten it because you love fudge filling, what's the probability the second piece will be filled with caramel? So because you've eaten a piece of chocolate, there are now only 14 left in the box. Did you eat a caramel? No, you ate a fudge. So there are still 3 caramel left out of the 14 chocolates in the box. Without replacement means the events are not independent. When you eat that first piece of chocolate, it affects what's going to happen with the second piece that you pick. So again, if we've got fudge first and then caramel second, fudge first is still 4 out of 15, but now the second piece, your box is reduced by a number. That the total number is now only 14, but there are 3 caramel. We can still multiply. We just said these are not independent. You know, 1 fudge is removed from the box. So if I wanted to put this into letters, this is the probability of A1. This is the probability of B2, given that A1 occurred. Because you took out that fudge. Okay, let's try again. Does the rule you cited in number 6 apply in the scenario in which you replace the first chocolate? Or in the scenario where you eat the first chocolate? So this was replacement. This was not replacement. And the rule we cited in number 6 is two events happening, A and B is the probability of A times the probability of B, only if the events are independent. So which of these events are independent? When you replace the first chocolate or when you eat the first chocolate? You should have said the one with replacement. We can do that because it's independent. Not independent when you eat one and reduce the number of chocolates in the box. So your mom has a rule that whatever you take, you eat. So whenever you take the chocolate from the box, you eat it rather than replace it. What does P1 and B2 B1 and A2 represent? All right, well, wait. A was fudge and B was caramel. Oh, why am I having, okay, caramel. So this is saying this is the probability of getting a caramel first and then a fudge second after you eat the caramel. So you eat the caramel or throw it out if you don't like it, I guess. So to calculate this, this is probability of caramel times the probability of a fudge, given that we already ate the caramel. There are 3 out of 15 caramels in the box. There are 4 fudge, but only 14 left. Make this bigger. So that gives us 12 out of 210 as the probability. Oh, now they're telling us about the coconut again. All right, let's look back at the total sample set. They got 3 caramel. We've got 2 cherry, 2 coconut, 4 chocolate whipped, and 4 fudge. Okay. That's our 15 chocolates in the box. So if C represents the coconut, what is the probability of getting a fudge and then a coconut? You have to eat the fudge. So that's the probability of fudge times the probability I get a coconut second after I've eaten the fudge first. There are 4 fudge out of 15. I've eaten a chocolate, so there's only 14 left, but how many are coconut? That's 2. All right. Probably the first and the second are both chocolate whipped. So there are 4 chocolate whipped out of 15, but then I've eaten one, so there's only 14 left, but I also want another chocolate whip. So I've eaten one of the 4, so now there's only 3 chocolate whips left. So I was going to put that in symbols. That's the probability of getting a whipped first times the probability of getting a whipped second, given that I already got a whipped first. So let's write a more general rule. In the case, can you write a more general probability rule that applies in case of replacement? Can you prove it and how to connect it to number 6? Okay, let's just write a general rule. So we're going to say this is the multiplication rule for two events if independence is not known. We just don't know if they're independent or not. So the probability of A and B occurring is the probability that A occurs times the probability of B occurs given that A has already occurred. All right, page 41. Let's practice these formulas. For each of the following, write the probability as the intersection of two events, then indicate whether they're independent or dependent and calculate the probability. Probability of selecting 6 from the first draw and a 7 on the second when the two balls are selected without replacement from a container with 10 balls numbered 1 through 10. So that's the probability of a 6 times the probability of getting a 7 given that a 6 already occurred, because without replacement is not independent. So there are 1 out of 10 that are 6, and then 7, there's still 7, 1 ball in the container labeled 7, but now only 9 remain. Okay, so with replacement now, same scenario, we're picking a 6 and then a 7, like the lottery. With replacement means they are independent events. So we can do the probability of selecting a 6 and the probability of selecting a 7. 1 out of 10 or 6, 1 out of 10 or 7. That's 1 out of 100. The probability that two people selected at random in a shopping mall on a very busy Saturday. So what they're implying here is a large population, a large sample space. Have a birthday in the month of June. Assume that there's 365 days are equally likely and ignore a leap year. So that would be the probability of June times the probability of June. Does the second person's birthday get affected by the first person's birthday? No. So there are 30 days in June and another 30-day possibility out of a whole year. I'm not going to multiply them together. That's just how we'd calculate it. The probability that 2 socks are selected at random from a drawer containing 10 black socks and 6 white socks. What's the probability they will both be black? All right, so that's probability of getting a black first and the probability of getting a black second, given that I got a black first. So 10 out of 16 socks, but now there's only 9 black that remain out of 15 socks that remain. All right, now we've got a gumball machine. The gumball machine has 4 different flavors: apple, grape, orange, and cherry. There's 6 of each flavor. When you put 50 cents in the machine, you get 2 gumballs that come out. C1 means you got a cherry first, and then a C2 means you got a cherry second. What does C2 given that C1 means in this context? The second gumball is cherry if it is known that the first gumball was cherry. Find C1 and C2. So they're going to come out at the same time. So the probability of getting cherry first, the second gumball is affected by the first one. All right, there are 6 of each flavor. So there are 24 gumballs to start, and then 23 after I get the first one. 4 are cherry, and then only 3 cherry. Oh no, 6. Oops. 6 are cherry. I've already gotten 1, so now there's only 5 left for after that. So in your calculator, well, 6 times 5, we know that's 30. 24 times 23, 552. All right, find A for apple first, and then getting a grape second, given that I got an apple first. So there are 6 out of 24 apples. Only 23 remain, but still 6 are grapes. All right, last problem. Below are the approximate percentages of the different blood types for the people of the United States. Consider a group of 100 people with a distribution of blood types consistent with these percentages. If 2 people are randomly selected with replacement, what's the probability that both have type O? So if they're being replaced, that's the probability of type O times the probability of type O. So that's 44% multiplied by 44%. So 19.36%. The first person has type A, and the second person has AB blood. Still with replacement, so type A is 42%, AB is only 4%. Type that in your calculator. And we get about 18.48%. All right, your homework is page 43 to 47. Tomorrow we'll bring some quiz review before the end of this second part of our probability unit.